You settle softly into your quiet space, a cozy refuge from the day's bustle. Imagine the tiniest worlds nested inside and all around you. Realms where particles dance in waves of possibility, where certainty fades and wonder blooms. This is an invitation to relax, to drift gently, and to meet the quiet magic of quantum physics, not as a puzzle to solve, but as a dream to float within. There's a softness to this moment, isn't there? Your body sinking slowly into the comfort beneath you, your breath tracing a gentle rhythm as the day exhales away. Here, in this hush, you find a new kind of space, a stillness that invites your mind to wander not into a world of noise but into a world woven delicately with whispers of possibility. You are about to embark on a journey, a quiet exploration to the edges of reality itself, where the rules you know start to shimmer and bend like twilight waves. Close your eyes if you like, or soften your gaze as you listen. Feel how your senses begin to relax, how your heartbeat steadies. This story is a gentle one, about the strange, beautiful world of quantum physics, the invisible dance of the tiniest building blocks that cradle everything you know. You don't need to be a scientist or a mathematician here. You need only your curiosity, your willingness to imagine, and your quiet breath. Now, picture a ballroom, vast, endless, filled with dancers. But these dancers aren't people. They are the particles that make up your very flesh and thoughts. The sunlight pouring through your window, the gentle hum of your own breath. Here, in this ballroom, the dancers move according to a different rhythm than the one you're used to. They don't march in predictable lines. Their steps are waves, shadows, possibilities, sometimes stepping through to places at once, sometimes hesitating until someone watches. You might wonder, how can something so tiny, so elusive, possibly matter to you? The answer is tender and simple. Everything you are, everything you touch, everything you love is woven from these quantum dances. Your body's warmth, your mind's flickering thoughts, the stars that light the night, all of it shaped by the soft music of these particles, hidden from view, whispering their secret song. Let's start with a thought. Imagine you're in a dark room. Someone tells you there's a tennis ball in the corner, but you can't see it. You reach out, your fingers brush something round and firm. There it is, solid and certain. This is the world you know well. Things have places, people have shapes. Your cup stays on the table. But now, imagine instead that the thing in the corner is tiny, much tinier than anything you've ever seen. So small it's almost a ghost. It might be in the corner, or it might be just a little bit away, or it might be in several places at once, all shimmering in a cloud of maybe. This is the strange way the quantum world works. Particles like electrons don't have fixed places the way your tennis ball does. They live in clouds of possibility, beautiful, blurry, shimmering places of could be and might be. Until you reach in with a measuring hand, they don't pick just one spot. It's as if they hold all their options open, dancing lightly between states. And isn't that a curious thing? A tiny particle saying maybe instead of yes or no. It teaches us that certainty, the kind we cling to every day, is a luxury of scale. When enough particles gather, the maybes cancel out, and the world becomes solid. The table, your hand, the gentle rise and fall of your chest. But down here, at the smallest scales, reality is a garden of maybes, invitation to wander. You might feel a flicker of unease at this uncertainty. After all, you like your world to be steady, your steps predictable. But what if this gentle blur beneath it all is not weakness, but a kind of grace? What if the universe is a dance not of strict rules, but of flowing possibilities, each softly choosing form just as you might pick the color of your dreams before you drift off to sleep? Now, let me share with you a tale, one of the oldest, quietest, and most magical stories in all of science, the double slit experiment. Picture a simple setup, a wall with two tiny slits, almost like doors, just big enough for the smallest of guests to pass. On one side, you send out a beam of tiny particles, electrons, one by one, like whispers sent across a silent room. You might expect the particles to pass through one slit or the other, showing up behind the wall in two neat clusters, like little footsteps left on sand. But the universe has other plans. Instead of two clusters, an intricate pattern emerges on the wall behind bands of light and shadow, as if waves are overlapping, rising and falling in gentle ripples. It's as if each particle isn't a tiny dot, but a wave stretching through both slits at once, playing a quiet game of hide and seek with itself. When you aren't looking, the particle simply waves, spread out, uncertain, full of potential. But when you peek carefully to see which slit it goes through, the wave shatters and the particle picks a side, forcing the ripples back into stepping stones. Isn't that a delicate kind of magic? How simply the universe reminds us that the act of observing, of reaching out with curiosity, shapes the story. We are not just quiet witnesses, but gentle participants in the unfolding of reality. You, with your breath and your stillness, are part of this quantum dance, nudging the wave into becoming a particle, possibility into reality. And so, as your eyelids grow heavy, picture those waves, not rushing, not crashing, but flowing gently, a soft song under every quiet moment. Feel how the strange and wonderful rules of this tiny realm don't roar but whisper, weaving a tapestry so subtle that only with calm eyes can we begin to see. Tonight, as you drift, let your mind float in the cloud of quantum maybes. Perhaps you are a wave spreading softly across infinite possibilities, uncollapsed, shimmering. Or perhaps you are the observer, quietly inviting the universe to answer just for you. Either way, the story gently unfolds. And when you wake, maybe the world will seem just a little softer, a little more mysterious, a little more alive with maybes, as if the universe itself is breathing beside you, ready to tell its next secret when you come again. For now, rest easy in this quiet place of wonder, wrapped in the gentle embrace of possibility, your heart gently stepping in time with the quantum beat, a lullaby for the curious soul. What do you think the little particles dream about when no one is looking? As your thoughts drift, hold on to that question lightly, like a shell on the shore waiting to be turned. In the quiet heart of your being, uncertainty hums softly like a lullaby, an ever-present companion shaping the way that tiniest particles and your thoughts alike find their place. This chapter gently explores the elegant uncertainty principle, the delicate balance of knowing and not knowing, and how this soft blur of possibility cradles the stability of everything around you. Like music and shadows, certainty and mystery entwine, inviting you to rest in the dance between. Imagine your breath flowing like a slow, steady tide, the rise and fall of your chest mirroring the ebb and flow of a vast sea. Within this sea of calm, something extraordinary hides a quiet invitation to explore the gentlest yet most profound mysteries of existence. This is the dance of uncertainty, and tonight, you are invited to sway softly with its rhythm. In your everyday life, you move with ease through a world built on certainty. If you place your hand on a warm cup, you know it is there, solid and steady. If you watch a leaf fall, you expect it to trace a predictable arc to the ground. But beneath this familiar stage, at a scale so small it invites awe and wonder, the rules shift. Certainty becomes a delicate shimmer that cannot be grasped with firm hands. Here, nature hums a different tune, a symphony of probabilities, where knowing one thing exactly means letting another drift softly into mystery. This tender balance is known as the Heisenberg uncertainty principle. It tells us that for the tiniest particles dancing just beneath the surface of your world, electrons, photons, and their kin, the more precisely you hold one truth, the more the other slips away like a mist. For example, if you know exactly where an electron is, you cannot know precisely how fast it is moving or where it is headed. And if you measure its speed exactly, its precise location becomes a gentle blur. To grasp this, imagine trying to photograph a firefly on a dark summer night. You shine your flashlight to catch its glow, but the light startles it, and it darts away. You might snap a sharp image of where the firefly was, but in that instant, you lose track of its motion. Alternatively, if you watch its path to understand its speed and direction, you must let go of pinpointing where it began. In the quantum realm, this is not a limitation of your camera or your eyes, but a fundamental whisper of nature itself. This principle is not chaos or randomness, but a structured dance, one where facts gently trade places like partners in a waltz. It reshapes the very act of knowing. It tells us that the universe, at its most intimate level, refuses to be pinned down by sharp lines and hard edges. Instead, reality appears as a soft watercolor painting, where colors blend and shapes emerge only when we look closely, then fade again when we stop. But why does this matter to you, here in the soft quiet of your room? It matters deeply because uncertainty is the reason your world is stable and full of life. Picture the atom, the tiny building block of everything you can touch, see, and be. The atom's heart is a nucleus, a dense center of protons and neutrons. Surrounding it buzz electrons that, by rights, should spiral inward, collapsing into the nucleus like rainwater, rushing down a drain, yet they don't. The uncertainty principle gently pushes back. If an electron were to squeeze into a tiny spot near the nucleus, its speed and energy would skyrocket to impossible heights, forcing it to flee outward again. This subtle dance between position and momentum creates a delicate balance, a cosmic breathing space where electrons hover in fuzzy clouds, orbitals, shaping the size and structure of atoms themselves. Without this serene uncertainty, matter, as you know it, would unravel. That this dance also invites you to see your own body differently, as a vast, wondrous sea of particles and waves, all humming with this gentle blur of possibility. Every breath you take, every beat of your heart, every flicker of thought is built on atoms held together by the soft pulse of uncertainty. It is as though your very existence rests on a quiet promise that beneath the firm surface of things lies a dreamlike realm, full of maybes and might bes, a shimmering foundation of potential waiting, patiently to be realized. Let's slow down again and feel the rhythm of this dance. Imagine a tuning fork struck softly in a silent room. The pure note lingers, clear and steady. Now imagine striking it quickly and letting it fade. The note becomes less distinct, a blend of whispers rather than a single clear tone. In the quantum world, this is the essence of uncertainty. The more exact the moment you fix, the less exact the note, the momentum becomes. The more certain the energy, the fuzzier the time. This is why the quantum world resists the neat, tidy boxes we might expect. It invites you instead to wander through its soft borders, to trust in its gentle unfolding. There's a poetic kindness in this, not a limitation, but a freedom, a kind of breathing space where life can unfold with grace and purpose, where the very rules of existence embrace imperfection and possibility. You might wonder, how does this mysterious uncertainty add up to the world you wake up in, the room around you, the chair that holds your weight? The truth is that the fuzziness of particles at tiny scales fades away when billions upon billions gather together, smoothing out into the solid, reliable forms you know. It's like watching the ocean from afar, a surface smooth and steady, but stepping closer to see waves, ripples, and fluctuations hidden beneath. This idea reassures us that the uncertain quantum dance beneath is not wild chaos but a harmonious foundation for the familiar world. It allows atoms to resist collapse, for molecules to form, for chemicals to behave with predictable grace, and for you to rest peacefully in your bed, feeling the quiet power of this principle. You might find your mind wandering gently the way thoughts do when they drift between wakefulness and sleep. You float between what is and what might be, the soft edge between knowing and wondering. And there, in that space, the uncertainty principle invites you to rest, to release the need for perfect answers, to welcome the mystery as a friend, to let the universe and your thoughts shimmer side by side. As your eyelids grow heavier, imagine the grand cosmic dance continuing beyond your sight, particles swirling in waves of probability, casting gentle shadows across the unseen landscapes of existence. Each moment of measurement, each breath, each glance collapses possibilities into realities, a never-ending ballet of becoming. Now, before we close this chapter, let me leave you with a quiet story, a metaphor for the dance you inhabit. Picture a forest where the paths beneath your feet shift as you walk, sometimes firm and clear, sometimes soft and uncertain. The trees sway in time with your thoughts, the leaves whispering secrets that ripple like waves in a gentle stream. You don't know where the path will lead, but you trust its unfolding. The forest invites you to wander, to listen, and to be part of its story. That shifting forest is the quantum world you live within, soft, mysterious, full of endless possibility. And as you close your eyes, you become part of its gentle rhythm, dance of uncertainty cradling you, a lullaby for your dreaming mind. What might the path show you next? If you trust the dance of uncertainty and step gently into the soft unknown, hold that question lightly and breathe. Step softly now into one of the most enchanting and slightly mysterious corners of quantum physics, entanglement. This phenomenon weaves a delicate and invisible thread between particles, connecting them across any distance, be it centimeters, kilometers, or even light years, instantaneously. It's a relationship so profound that even Albert Einstein once called it spooky action at a distance. Imagine two electrons sharing a special bond, Like perfect dance partners in a cosmic ballet, they are prepared, so their quantum states, such as their spins, are intertwined. If one electron is found spinning up, the other must be spinning down to keep the total spin balanced. Now, separate these electrons across the globe, one in Paris, one in Tokyo. Measure the spin in Paris, and instantly know the spin in Tokyo, no matter how far apart they are. But how can this be? Does something travel faster than light? Here lies the subtlety. Entanglement does not allow faster-than-light communication. The measurement outcomes are fundamentally random and uncontrollable, meaning no message can be sent instantly through this quantum connection. Yet, the correlation between results defies classical intuitions and points to a universe more interconnected than everyday experience suggests. Experiment after experiment, from the EPR paradox tests to refined Bell inequality verifications, have confirmed entanglement is real. This challenges classical ideas of locality, that things far apart can't instantly affect each other. Entanglement stretches the very fabric of reality, reminding us that the universe is a subtle, interconnected tapestry. Entanglement is more than a curious quantum oddity, is a powerful tool. Quantum cryptography uses it to create unbreakable codes, where any eavesdropping disturbs the entanglement and reveals the intrusion like a silent alarm. Quantum teleportation, another astonishing application, allows the transfer of quantum information between particles over distance, underpinning future quantum networks and computing. This deeply relational aspect of existence invites us to rethink separation itself. In the quantum realm, being is to be entangled, to be part of a whole that spans space and possibly time. Moving from entanglement, the chapter gently unfolds the observer effect, the idea that observation is not a passive act but one that influences the very system observed. When we measure a quantum particle, such as an electron, the fuzzy cloud of possibilities, its wave function, collapses into a definite state. Unlike peeking at familiar things in your daily life without changing them, measuring a quantum system inevitably disturbs it. Like shining a lantern in a dark forest, startling a deer, quantum measurement nudges particles into choosing a particular state, out of a cloud of many potentials. What counts as a measurement, a conscious observer, a device, or an uncontrollable interaction with the environment, remains debated. Some early ideas proposed that consciousness collapses the wave function, but modern thinking favors the view that interaction with the environment, a process called decoherence, causes this collapse. Decoherence blurs the delicate quantum superpositions, causing systems to behave classically. This explains why large objects like cats and tables never appear in multiple states at once, even as tiny particles freely do. Yet, a deep and enduring mystery remains. Why do we perceive a single definite outcome when many outcomes could exist? Interpretations vary. Some say the wave function never collapses but splits the universe into multiple branches, while others propose spontaneous collapses or personal subjective views. Whichever view one holds, the observer effect reveals a participatory universe where the act of looking and measuring is woven into how reality unfolds. We, as observers, gently shape the story of existence. So as you lie quietly reflecting, imagine yourself not just as a witness but as a gentle participant in the grand unfolding of the cosmos, where every glance by you, every act of noticing, is a soft thread drawing possibility into reality. In this chapter, we dive into one of the most beautiful and puzzling ideas of quantum mechanics, superposition. This concept is like keeping your options open. A particle can exist in multiple states simultaneously until observed. Imagine flipping a coin. In everyday life, it's either heads or tails once it lands. But in the quantum realm, the coin can be both heads and tails at once, while it spins in the air. Similarly, particles like electrons can exist in a superposition of states, such as simultaneously having spin up and spin down. Before you measure a particle's state, it truly exists in this fuzzy, cloud-like blend of possibilities, described mathematically by a wave function. Upon measurement, the superposition collapses into one definite, stated spin-up or spin-down. The chapter also discusses the famous Schrödinger's cat thought experiment, which highlights the oddity of superposition when applied to everyday objects. In the experiment, a cat sealed in a box is linked to a quantum event, an atom, that can decay or not. Until the box is opened, the cat is described as being both alive and dead simultaneously. reflecting the atom's superposed state. Physicist Schrödinger introduced this to show how bizarre quantum logic seems if extended to macroscopic objects. In reality, large objects don't stay in superpositions for long because of dicoherence, interactions with the environment that collapse quantum fuzziness into definite outcomes. This is why we don't see toasts partially toasted or cats both alive and dead in everyday life. Superposition is not just a theoretical curiosity, it's the foundation of quantum computing. Unlike classical computers that store information as bits, either 0 or 1, quantum computers use qubits. Qubits can exist in superpositions of 0 and 1, simultaneously representing many possibilities. Because qubits can be in multiple states at once, quantum computers can explore vast numbers of possible solutions in parallel, offering exponential speedups for certain types of problems, such as factoring large numbers, optimizing complex systems, and simulating quantum physics itself. Building practical quantum computers is challenging, because qubits are delicate and prone to losing their quantum states through interactions with noise or heat decoherence. Maintaining stable superposition requires extremely controlled, ultra-cold environments and advanced technology. Despite these challenges, the promise of quantum computing is immense. It opens a new frontier in computation, blending logic and uncertainty, precision and possibility. This chapter introduces the Heisenberg uncertainty principle, a fundamental idea in quantum physics. Formulated by Werner Heisenberg in the late 1920s, it explains a profound limit on what can be known about a quantum particle in everyday life. We expect to know both the position and velocity, momentum of an object precisely, but at the quantum scale, this certainty breaks down. The uncertainty principle states that the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This is not due to flaws in instruments, but is an inherent property of nature. This principle arises because particles are described by wave functions. Sharp localization in space causes a spread in momentum and energy. A classical analogy is a musical note. A clear, long note has a precise frequency but vague timing, whereas a short note has an uncertain pitch. This principle has real consequences. For example, it prevents electrons from spiraling into atomic nuclei by forcing a balance between position and momentum uncertainty, stabilizing atoms and therefore matter itself. Though sometimes unsettling, this principle is an elegant part of quantum reality, implying that knowledge itself has boundaries and that the universe allows room for flexibility, openness, and beautiful indeterminacy. Quantum entanglement. The chapter then explores quantum entanglement, an astonishing phenomenon where particles become so deeply linked that the state of one instantly influences the state of another, regardless of distance, even across galaxies. Entangled particles, such as electrons with their spin, share a combined quantum state. Measuring one particle's spin immediately defines the spin of its partner. This phenomenon baffled Einstein, who called it spooky action at a distance. Importantly, entanglement does not allow faster-than-light communication because the measurement outcomes are fundamentally random, and classical communication is still needed to compare results. Experiments, starting in the 1980s, have repeatedly confirmed that entanglement is real and that any hidden variable explanations fall short. Scientists have entangled not just small particles but increasingly larger systems, pushing the boundary of quantum effects towards the classical realm. Entanglement is the foundation of emerging technologies like quantum cryptography for secure communication, and quantum teleportation, transferring quantum states via entanglement. Plus, classical communication. Quantum computers rely heavily on entanglement to process vast numbers of possibilities simultaneously. Entanglement challenges classical notions of separateness, implying that at the deepest level, reality is an interconnected tapestry, hinting at profound harmonies woven into the universe's fabric. The observer effect. The observer effect in quantum mechanics is the idea that the act of measuring or observing a quantum system fundamentally changes it. Observation is not just a passive act of revealing what is already there. It actively influences the state of the system. In everyday life, observing usually doesn't change what you observe, checking the weather or looking at your phone. But at the quantum scale, the act of observation unavoidably disturbs the system. For example, to detect an electron's position, photons may be bounced off it, but these photons also alter the electron's momentum. This leads directly to the uncertainty principle. Wave function collapse. Quantum particles don't have definite properties like position or momentum until they are measured. Before measurement, these properties exist as a range of probabilities described by the wave function. Measurement causes the wave function to collapse from this fuzzy spread of possibilities into a single definite outcome. This collapse is mysterious and one of the biggest puzzles in quantum physics. It's like the universe writing a story in pencil and an observation erasing all but one ending. What counts as a measurement? A key question. Does the wave function collapse require a conscious observer, person, or can any interaction cause it? Some early interpretations suggested consciousness was necessary to collapse the wave function, implying reality doesn't exist until measured by a mind. Most physicists today favor the view that collapse occurs due to interaction and entanglement with the environment, not consciousness. Decoherence is the process where a quantum system, once isolated, interacts with its environment, air molecules, photons, measuring devices, causing its quantum behavior to break down. The delicate superposition state spreads into the environment, and the system begins to behave classically. Decoherence explains why we don't see macroscopic objects, like cats or chairs, in superposition states. Remaining mysteries and interpretations with the questions remain. Why do we see just one definite outcome and not multiple? Why does the wave function collapse at all? Some interpretations reject collapse altogether. The many worlds interpretation suggests that all possible outcomes happen in branching, parallel universes, so the wave function never truly collapses. Others introduce objective collapse theories, where wave functions spontaneously collapse independently of observation. Another interpretation, cubism, views the wave function as a reflection of personal knowledge or belief, rather than objective reality. The role of the observer regardless of interpretation, the observable fact remains. Measurement or interaction changes the system. Observation in quantum mechanics is participatory. It shapes reality rather than just revealing it. We are not creating reality with our minds, but are deeply woven into the fabric of it as observers and participants. The classical world, what about large objects like the moon? They appear to exist independently of observation. This is because macroscopic objects constantly interact with their environments, causing rapid and constant decoherence. Their wave functions collapse so thoroughly and frequently that their quantum nature is effectively hidden, making them behave classically. This chapter invites a calm and reflective view of quantum measurement, the mysterious bridge between the fuzzy quantum world and the definite classical world we experience, highlighting the deep connection between observer and reality. What is superposition? Superposition is one of the most mind-bending ideas in quantum physics. It means that until something is measured or observed, a particle can exist in multiple states at the same time. A common analogy is a spinning coin in mid-air. It is both heads and tails simultaneously until it lands and you observe it. In quantum terms, a particle literally exists in a superposition of states until observed. Example: electron spin. Consider electron spin, a quantum property akin to a tiny arrow pointing up or down. When measured along a particular axis, the electron spin can be only up or down. Before measurement, the electron is in a superposition of both spin up and spin down. The electron is not undecided or 50/50ths. It is truly both simultaneously. The probabilities of each outcome are represented mathematically by a weighted combination of those states. Schrödinger's cat thought experimentations imagined a cat in a sealed box linked to a quantum event, radioactive decay. Until observed, the atom is in a superposition of decayed and not decayed states. That means the cat is also theoretically in a superposition state, both dead and alive, simultaneously. Schrödinger's point was to illustrate how strange quantum mechanics becomes when applied to everyday objects. In reality, decoherence caused by interactions with the environment prevents such macroscopic superpositions. Hence, no actual dead and alive cats exist. Importance and reality of superpositions. Superposition is not just a philosophical idea. It's verified by experiments and is fundamental to how atoms bond, light behaves, and stars shine. It challenges the classical idea of something having to be one thing or another, instead embracing a state of maybe. Our observations collapse the superposition into a single outcome. Before observation, all possibilities coexist. Quantum computing and superposition. Quantum computing harnesses superposition. Unlike classical bits which are strictly 0 or 1, qubits can be in of 0 and 1 simultaneously. This allows quantum computers to explore many computational paths in parallel, giving them extraordinary potential power. The exponential scaling of qubits means even a modest number can represent an enormous number of states at once. Quantum computing doesn't replace classical computing but complements it by tackling specific, complex problems more efficiently. Philosophical reflections. The idea that the universe or particles are in superposition until measured raises profound questions about reality. Some speculate whether the entire universe exists in a giant superposition of possibilities. Though mathematically precise and experimentally confirmed, the interpretation remains open and mysterious. Superposition invites us to let go of certainty and accept a world where existence can be many things at once until pinned down. Gentle conclusion. Each observation turns a cloud of possibilities into a moment of reality. Between observations lies a vast, quiet realm of maybe. This intrinsic uncertainty is a gentle reminder that reality is dynamic, fluid, and participatory. The quantum world calls us to appreciate mystery as a feature, not a flaw. Introduction to the uncertainty principle. The uncertainty principle, discovered by Werner Heisenberg in the late 1920s, is a quiet but profound reshaping of how we understand knowledge in the quantum realm. Unlike everyday life, where we can know both where something is and how fast it's moving simultaneously, at the quantum level there is a fundamental limit to this simultaneous precision. What does the principle say? It states that the more precisely you know a particle's position, the less precisely you can know its momentum, speed, and direction, and vice versa. This is not due to flawed instruments or difficulty in measurement, but a fundamental property of nature. The universe keeps some things forever blurred. Everyday analogy. Imagine trying to photograph a firefly in a dark room. Shining a light to see it exactly will startle and move it. You can catch its position, but disturb its momentum. Or, if you track its movement over time, you may lose exact information about its starting position. Mathematical aspect. The principle is often expressed as x asterisk delta p is greater than or equal to k, to delta x times delta p greater than or equal to reduced Planck's constant divided by 2. This represents a hard limit on simultaneous knowledge of position and momentum. Broader implications. The uncertainty principle also applies to other pairs, such as energy and time. This allows phenomena like virtual particles appearing briefly and contributes to processes from atomic behavior to black hole physics. Why it matters. Physically, one key consequence: electrons don't spiral into the nucleus, despite electrostatic attraction. If electrons were confined too tightly, their momentum uncertainty would cause them to have very high kinetic energy, pushing them back out. Stabilizing atoms. Chemistry and matter depend on this delicate balance. What it feels like the principle implies a world that's not sharp and rigid, but soft and blurry, where attempts to know one feature precisely cause fuzziness in another. It conveys a gentle invitation to accept fundamental limits on certainty. Everyday relevance. The effect is imperceptible at human scales, because quantum uncertainties are extremely small for large objects. At quantum scales, uncertainty dominates and defines what can be known. This principle draws a soft edge between possibility and measurable reality. Summary. The uncertainty principle is not chaos or randomness in the everyday sense, but a structured indeterminacy. It gently reminds us that we participate in shaping what can be known in this universe. Nature's fundamental makeup defies absolute precision, leaving space for flexibility, openness, and beautiful indeterminacy. Introduction to quantum entanglement. Quantum entanglement is a mysterious phenomenon where two or more particles become deeply connected. The state of one particle instantly affects the state of its entangled partner, regardless of the distance between them, even across galaxies. Einstein famously called this spooky action at a distance. How entanglement works: consider a pair of electrons prepared so that their total spin is balanced. If one electron is measured to have spin up, the other must be spin down, like a cosmic dance keeping perfect symmetry. These particles exist in a shared superposition. Their states are undefined until measured. When one is observed, the combined wave function collapses, and both take on definite, correlated states. Does entanglement violate relativity? It seems to defy the speed of light limit, because the effect is instantaneous no matter how far apart the particles are. However, no usable information or message travels faster than light, not violating relativity. Measurement outcomes are random, so you cannot control or send signals using entanglement alone. Historical context and experiments in Stein, Podolsky, and Rosen-Epi are challenged the completeness of quantum mechanics. Proposing hidden variables to explain entanglement, John Bell developed inequalities to test whether hidden variables could exist. Experiments from the 1980s onward overwhelmingly supported the standard quantum view. Entanglement is real and non-locality is fundamental. Entanglement beyond tiny particles. Experiments have entangled larger molecules, atoms, and even visible mechanical resonators. The boundaries between quantum and classical worlds are slowly being explored and expanded. Practical applications: quantum cryptography uses entanglement to detect eavesdropping and ensure secure communication. Quantum teleportation transfers the quantum state of one particle to another at a distance, relying on entanglement and classical communication. Quantum computing: entanglement links qubits, allowing enormous parallel processing capabilities beyond classical computers. Philosophical implications: entanglement challenges classical notions of separation and independence. At its core, reality may be an interconnected tapestry rather than isolated pieces. Entangled particles may maintain a connection across space and time, a deeper harmony woven into the fabric of existence. The observer effect explained. The observer effect in quantum mechanics is the idea that the very act of measuring or observing a quantum system fundamentally changes it. Observation is not passive at the quantum level. It's more like participation, where the measurement alters the system's behavior. For instance, to determine an electron's position, scientists might bounce a photon off it, but that photon also changes the electron's momentum. Measurement and wave function collapse. Measured quantum particles exist in a superposition of states, described by a wave function representing probabilities that an observation causes the wave function to collapse into a single definite state. This collapse is mysterious and suggests reality is shaped by the process of measurement itself. What counts as a measurement? Some early ideas suggested conscious observers were required for collapse, but this view is largely rejected today. Most physicists believe that any irreversible interaction with the environment and entanglement with surroundings is enough to produce collapse. This process is called decoherence, where the quantum system loses its delicate superposition by interacting with countless particles around it. Decoherence: from quantum to classical decoherence, explains why we don't see quantum superpositions in everyday life. Interaction with the environment quickly destroys them. Large objects, like cats, are constantly interacting with the environment, so they behave classically and not as fuzzy quantum superpositions. Interpretations and remaining mysteries. Decoherence: fundamental questions remain, such as why only one outcome occurs. In measurement, the problem of outcomes. Alternative interpretations include many worlds interpretation. The wave function never collapses. All outcomes happen in branching universes. Pilot wave theory: particles have definite positions guided by a pilot wave. Objective collapse theories: wave functions collapse spontaneously due to physical processes. Cubism: quantum Bayesian. The wave function represents personal knowledge or beliefs rather than an objective reality. Participatory reality: the observer effect suggests reality is not fixed, but shaped through interaction and measurement. Observers do not create reality with their minds, but play a role in how it unfolds. Everyday objects like the moon remain real independently because they're quantum states. Decohere constantly due to environmental interactions. Final thought: at the smallest level, reality is a quiet ballet of maybes. Every measurement is like plucking one thread from a tangled web of possibilities and making it real. Through this lens, you, as an observer, are a gentle participant in the unfolding story of the universe.